There's a version of this video circulating right now claiming scientists fed images of ancient Egyptian granite cutting marks into an AI system called Grok, and that whatever it concluded left everyone watching genuinely shocked. Some versions claim the AI determined the cuts were too precise for any known ancient hand tool. Others claim it flagged the tool marks as evidence of a lost, more advanced technology entirely, sometimes framed as proof of some vanished civilization that predates the Egyptians we know from the historical record. A few versions go further still, claiming the AI compared the tool marks to modern industrial machining and concluded the precision simply couldn't be explained by anything short of powered rotary equipment. If you go looking for the actual research team behind any of this, the real transcript, the real institution, you'll find exactly what you found the last time someone tried to sell you a fake AI archaeological breakthrough. Nothing. No named scientist, no verifiable session. No published finding anywhere. It's invented, built off the exact same recycled formula as every other fake Grok video currently making the rounds. Here's the frustrating part, though, and it's worth sitting with directly. The real, actual explanation for how ancient Egyptians cut granite is already a genuinely fascinating, decades-long scientific story, complete with a real controversy, real competing theories among real Egyptologists, and even a real, still debated mystery object sitting in a museum in London that nobody has ever fully explained to everyone's satisfaction. You don't need a fabricated AI conclusion to make this interesting. The actual history already has more than enough intrigue built in. And let's start with the basic problem, because it's worth restating clearly. Granite is an extremely hard igneous rock, and ancient Egyptian metalworking throughout the Old and New Kingdoms was built around copper and bronze, both metals dramatically too soft to cut into granite, directly the way a modern steel or diamond-tipped blade would. So the question archaeologists have spent well over a century trying to answer isn't whether the Egyptians cut granite, since the finished results are sitting in temples and museums all over the world. It's specifically how they managed to cut, drill, and shape one of the hardest natural materials available to them, using tools made from some of the softest metals known to ancient metallurgy. The mainstream answer, developed and refined over decades of actual hands-on experimental archaeology, centers on a genuinely clever workaround, using the metal tools not as cutting blades in the traditional sense, but as carriers for a much harder abrasive material, specifically loose quartz sand. Quartz sits considerably higher than copper on the mineral hardness scale, hard enough to actually grind against and wear down granite, even though the copper tool itself never touches the stone with enough hardness to cut it directly. This is actually the same basic principle behind sandpaper, or a modern lapidary saw used for cutting gemstones, where the blade itself is rarely the hardest material doing the actual cutting work. It's simply the mechanism that drives a harder abrasive substance repeatedly against the target material until enough of it wears away. In practice, this meant Egyptian craftsmen used copper saw blades or hollow copper tubes for drilling circular holes, dragged or rotated back and forth across a bed of loose quartz, sand kept wet or dry, depending on the specific technique, letting the sand itself do the actual abrasive cutting work while the copper simply provided the mechanical motion and pressure needed to drive the sand against the stone. Researcher Alfred Lucas, working in the early 20th century, and later Dennis Stocks, conducting much more extensive hands-on replication work decades afterward, both independently arrived at broadly similar conclusions about this basic mechanism, even as they disagreed on some of the finer procedural details, such as whether the sand was typically kept wet or dry during actual cutting. Physical evidence for exactly this process survives in multiple Egyptian museum collections today. At the Patry Museum in London, a 4th Dynasty basalt fragment catalogued as UC 116033 still contains visible rock tailings and sand residue directly inside its original saw cut, essentially a frozen snapshot of the cutting process, interrupted mid-task and never cleaned up. It's a genuinely remarkable piece of physical evidence, precisely because it wasn't left behind as any kind of intentional demonstration or record. It's simply an object where the ancient craftsman's work was interrupted, and whatever debris happened to be sitting inside the cut at that exact moment was preserved by accident for the next 4,500 years. According to research compiled by archaeologist Dennis Stocks, who spent years conducting hands-on experimental replications of ancient Egyptian stoneworking techniques, this combination of copper tool and loose quartz sand abrasive was very likely the dominant method used to cut and shape hard stone across most of ancient Egyptian history. Drilling circular holes and hollow cores followed a closely related process, using a hollow copper tube rather than a flat blade. Egyptian craftsmen had a well-documented ability to manufacture copper and bronze tubing, evidenced by surviving cylindrical vessels and plumbing fragments recovered from multiple sites, with wall thicknesses on these ancient copper drilling tubes estimated at somewhere between 1 and 5 millimeters based on the tubular slots they left behind in worked stone, and researchers have confirmed that casting copper tubes of this thinness was well within the capability of Egyptian metalworkers using simple sand molds. Stocks's experimental work demonstrated a plausible working method. A bow-driven drill, similar in basic concept to a bow drill used for starting fires, spun the copper tube back and forth, driving it down into a bed of loose quartz sand poured directly beneath the tube's cutting edge. In Stocks's reconstructed experiments, this bow and tube setup produced roughly 120 full rotations per minute, alternating 60 rotations clockwise with 60 rotations counterclockwise as the bow was drawn back and forth, requiring a downward force of only around 1 kilogram per square centimeter to actually initiate cutting through the granite via the sand's abrasive action. In some of these reconstructed drilling experiments, 3 separate workers were needed to operate the full setup, 2 working the bow from either end, while a third held the drill steady and applied consistent downward pressure at the top, a coordinated multi-person task that itself offers a small window into how Egyptian workshops likely organized labor around these specialized stoneworking techniques. The physical results of this technique survive today in the form of granite drill cores, cylindrical plugs of stone left behind inside the hollow copper tube after a hole had been drilled, later snapped off and discarded once the tube was removed. Sir William Flinders Petrie, one of the founding figures of modern Egyptology, recovered numerous examples of these cores during excavations in the late 19th and early 20th centuries, including specimens from the Giza Plateau itself, and many are preserved today at the Petrie Museum at University College London, alongside spy holes and coring marks documented at other sites, including Djoser's Step Pyramid Complex at Saqqara and the actual granite sarcophagus inside the Great Pyramid's King's Chamber. Now here's where the real legitimate scientific debate actually enters the picture, and it's worth walking through fairly, because unlike a fabricated AI headline, this is a genuine disagreement that has played out in published research for decades. Some of Petrie's recovered granite cores show a distinctive spiral groove wrapping around their surface, and Petrie himself measured the spacing of that spiral, calculating what's called a feed rate, essentially how far the drill descended into the stone during each single rotation. On at least one particularly striking core, that feed rate worked out to roughly 1/10 of an inch of penetration per revolution, a rate that struck Petrie and later researchers, including engineer Christopher Dunn, as remarkably fast for a technique relying purely on loose sand abrasion and modest hand-applied pressure. Dunn, who has spent considerable time personally examining these cores at the Petrie Museum, has argued in his own published work that no modern attempt to replicate this specific core using a copper tube and loose sand abrasive has managed to reproduce that same combination of depth, efficiency, and spiral consistency, and he's proposed that ancient Egyptian craftsmen may have possessed some additional technique, perhaps a harder drill tip material, mechanical amplification through levers or counterweights, or some other refinement that hasn't survived in the archaeological record that allowed for considerably more efficient cutting than a simple sand and copper setup would predict. In his own writing, Dunn has gone further, suggesting the precision visible on this particular core implies a level of control and consistent downward force that feels, to him, more consistent with some kind of mechanized system than with a purely manual operation directed by hand. It's important to present that argument honestly, because Dunn isn't simply inventing tool marks that don't exist. The cores are real, they're on public display, and the spiral groove pattern he describes is a genuine, measurable physical feature. Where mainstream Egyptologists and experimental archaeologists diverge from Dunn's conclusions isn't over whether the marks exist, but over what they actually prove. Dennis Stocks and other researchers who have conducted their own hands-on experiments generally maintain that variations in feed rate, spiral consistency, and cutting efficiency can plausibly result from differences in exactly how much pressure was applied, how coarse or fine the quartz sand grains happened to be, how frequently fresh, unworn sand was added during the drilling process, and even natural variation within the granite itself, factors that are extremely difficult to precisely control or replicate centuries later using modern reconstructed tools in unfamiliar hands. Mainstream researchers also point out that Petrie's own single, most cited measurement represents one core out of many recovered examples, and that using a single outlier data point as proof of an entirely undiscovered ancient technology runs into an obvious statistical problem. It isn't representative of the broader, more consistent pattern seen across the rest of the surviving cores, most of which show feed rates and consistency levels well within what experimental replication using sand and copper has actually managed to achieve. In a detailed 1983 study specifically designed to help settle an earlier version of this same disagreement, originally a dispute between Petrie himself and a later researcher named Alfred Lucas over whether the abrasive had been used wet or dry, experimenters found that using loose sand or crushed quartz, whether wet or dry, as the abrasive between a copper tool and the stone, reliably produced exactly the kind of concentric cutting lines seen on the original ancient cores, While other tested abrasive methods failed to reproduce those lines at all, evidence that mainstream researchers point to as strongly supporting the sand abrasion explanation as fundamentally correct, even if the exact ancient technique for controlling pressure and feed rate hasn't been perfectly reverse engineered down to the last detail. That's genuinely how legitimate scientific disagreement is supposed to look. Real named researchers, working from the same physical evidence, publishing their specific methodologies and results, disagreeing over interpretation and efficiency, rather than over whether the underlying evidence exists at all, and continuing to refine their conclusions as new experimental data comes in. Nobody in this actual debate is claiming a chatbot analyzed a photograph and delivered a shocking verdict nobody could explain. They're measuring feed rates, testing abrasives, running actual drills through actual granite, and comparing their results directly against artifacts anyone can go examine for themselves in a public museum. It's worth pointing out, too, why this particular disagreement has persisted for so long without being definitively settled one way or the other, because that persistence itself gets misread and exploited by exactly the kind of content this video is responding to. Ancient stoneworking techniques don't leave behind instruction manuals. Egyptian craftsmen had no reason to write down methods that were, to them, completely ordinary. Well-understood trade knowledge passed down through direct apprenticeship rather than documentation. Modern researchers are left reconstructing a lost, oral craft tradition using nothing but the finished physical evidence and their own best attempts at replication, and replication experiments conducted by people without a lifetime of specialized training. In a specific ancient craft, will naturally struggle to perfectly match the efficiency of workers who spent their entire working lives mastering these exact techniques. That gap between modern replication attempts and ancient results isn't necessarily evidence of some lost superior technology. It's just as plausibly evidence of an enormous skill gap between a modern researcher attempting a technique for the first time and an ancient craftsman who trained in it since childhood. Mainstream researchers generally find that explanation considerably more parsimonious than assuming an entire, otherwise completely undocumented technological tradition existed and then vanished without leaving any other trace anywhere in the archaeological record. It's also worth understanding the broader stone-cutting toolkit the Egyptians relied on beyond just sand and copper sawing and coring, because granite work wasn't a single uniform technique applied identically in every situation, but rather a whole suite of complementary methods, each suited to a different stage of the work. For flat surfaces and larger-scale bulk removal, workers frequently used dolerite pounding stones, a volcanic rock naturally harder than granite, essentially bashing and crushing the granite's surface into powder rather than cutting it in any conventional sense. A technique still visible today in the trenches surrounding Aswan's famous unfinished obelisk, where hundreds of these hand-sized dolerite balls remain scattered exactly where ancient workers left them. For more detailed, controlled work, including inscribing hieroglyphs directly into finished granite surfaces, evidence suggests Egyptian craftsmen used flint chisels, a naturally occurring stone hard enough to engrave granite directly, driven forward using dolerite hammers rather than the softer wooden mallets used for working limestone. A 15-inch flint chisel was even recovered from the pit containing Khufu's ceremonial boat, physical confirmation that this specific tool type was genuinely part of the era's actual working toolkit, not merely a theoretical proposal reconstructed after the fact. Some researchers have also pointed to evidence suggesting controlled use of heat as a supplementary technique in certain granite working contexts, similar to the fire cracking method, sometimes proposed for the initial quarrying phase at Aswan. Heating a localized section of granite and then rapidly cooling it can cause internal stress fractures to form along fairly predictable lines, since different mineral crystals within the granite, quartz, feldspar, and mica among them expand and contract at slightly different rates as temperature changes. While this technique appears to have been more relevant to the bulk quarrying process than to fine surface cutting, it adds yet another layer to the overall picture of a genuinely varied, adaptable ancient stoneworking tradition, one that combined mechanical abrasion, controlled impact, and in some cases thermal stress, rather than relying on any single universal method for every task. So when you put the complete picture together, dolerite pounding for bulk removal, copper saws and quartz sand for precision cutting, hollow copper tubes, and the same quartz abrasive for drilling clean circular cores, flint chisels for fine detail work, and possibly controlled heating for certain large-scale quarrying tasks, you get a coherent, physically evidenced, experimentally tested explanation for how ancient Egyptians actually worked one of the hardest stones available to them, using only the materials genuinely available during their own era. There's a real ongoing conversation about exactly how efficient some of these methods were, and whether every last detail has been perfectly replicated by modern experimenters. But that conversation happens between named researchers, using published data, examining real artifacts sitting in real museums, not through some invented chatbot conversation that conveniently no one can ever actually verify. So the next time you see a video claiming Grok or any artificial intelligence uncovered some shocking, unexplainable truth about how the Egyptians cut granite, ask the same question worth asking every single time this exact template resurfaces. Where's the actual research, the actual scientist, the actual data anyone could go check for themselves? In the real version of this story, all of that already exists, sitting in the Petrie Museum, in Dennis Stocks's published experimental results, in the trenches at Aswan, and in a 15-inch flint chisel pulled directly out of Khufu's own boat pit. That's not a machine's shocking verdict. That's just patient, evidence-based archaeology, still working out the finer details of an ancient craft, exactly the way real science actually operates. There's a broader point worth carrying away from this one, the same point that applies to every fabricated AI discovery video circulating right now, whatever ancient mystery it happens to be attached to this particular week. Real unresolved questions in archaeology are genuinely interesting precisely because they remain open, debated by named people using real evidence, refined slowly over decades rather than solved instantly by a single dramatic reveal. A chatbot conversation that supposedly settles one of these debates in a single afternoon isn't actually offering you a more complete answer than the real scientific literature. It's offering you the illusion of resolution, borrowed from a genuine, ongoing scientific process it never actually participated in, repackaged as a shocking discovery specifically because shocking discoveries perform better than honest uncertainty ever will.